I
Ye-
hope everyone can hear me.
Yes, sir. Yes, sir.
Okay. Yeah. So good afternoon,
Yes.
everyone. And thank you, Pandav team, for inviting me to join this very first event, International Olympiad, which is on simulations. Yeah. It is interesting to see such an activity which have never been done and by someone like a Pandav, which is starting up, growing up. That is even more interesting to see that. Yeah. The problem selected was also very nice sedimentation regarding electrical fields and then further regarding the turbo machinery. It's very nice to have such problems as they cover wide variety of the fields and the audience are also like a or the participants can also cover a wide fields of interest there. Okay. So thank you for inviting, and I will just have like I think I'm given 10 to 15 minutes, so I will try to wind up within 10 to 15 minutes. We'll introduce some basic concepts on the modeling and simulations, and some industrial example which I can show from the existing literatures there. Okay, so I will share my PPT for that just to just it out. I hope it is visible to everyone.
Yes, sir. It's visible.
Okay, yeah,
Yes.
thank you. Yeah. Yeah, so good afternoon, everyone. A brief talk on the importance of the modeling and simulation in industrial engineering and design that I will discuss about. Myself from Prakash Bharti. I am currently working as professor in Department of Chemical Engineering at IIT Roorkee. Uh, I do not have any outline for the talk, just for some reasons, and we will go through that whatever contents that come up. It is also some purpose that we don't want to discuss what outline is so that you make a pre-mind, but let's go through the content what we can discuss it out here. Okay. So the first thing comes out what mathematical modeling is. Of course, like many participants which are here, they have been doing the mathematical modeling. They have been looking how to solve the engineering problem. But what exactly is mathematical modeling that I will start with? So generally, like there are three parts of the mathematical modeling that there may be a mathematical model, there may be a beautiful engineering, and then we can say like what mathematical or the excellent or good mathematical models are. So first question comes about the mathematical model. We can simply say that approximation of some physical phenomena in terms of the quantitative way. So for example, that if there is a mass flow, that how we can quantify that mass by some utilizing some existing approaches, existing relations therein. Then the next part comes out what is beautiful engineering. So since we know that the mathematical models will have some approximations through which that actual problem can be represented in terms of the mathematics. And so the beautiful engineering comes out like a, how good the concept that we develop, what is the engineering approaches that we utilize, how do we image that concept, and what creativity we can introduce therein. So if we have a blend of all four things that the model that we develop out or the solutions that we obtain from this is called as a beautiful engineering. So for example, like in everyday life, we see the mobiles, which is like a beautifully engineered. They are designed starting from a very large set to like we have a very small sets therein. So that they are based on the concepts, engineering, imagination, and the creativity and the need that we have. Then finally comes out what is good mathematical model, which is nothing but like a how we can miniaturize that system. So the beautiful engineering on the miniaturized level, we can say that it is a good mathematical model, which is giving us a product which is very sophisticated product, very useful project therein. Keeping in mind those approaches like we need to solve that, the process of model building and solutions can then be discussed it out as the modeling requires a solution of some problem. And so the very first point that comes out what we need to solve, how sorry. So the first point that comes out, what do we need to solve, how do we need to solve? So we discuss out the physical and engineering problem. Let me just select the pointer. Yeah. So the first thing comes out like the real life. What do we want to model it? And so the physical and engineering words that starts with we visualize that and we try to look at what are the phenomena that may be available to correlate with the physics, the real life example that we want to simulate. Once we know the phenomena, we look for the assumptions that is required to utilize these phenomena, and based on that, we come up with some conclusion like what is the possibility of modeling the systems therein. By having the first stage done, we look for the physical approaches or the conservation laws. And so we write down there may be a mass conservation, there may be a momentum conservation, or there may be the energy conservation. And so we suitably apply the conservation law. We write down the other necessary laws as well that may be relating to the heat or mass transfer, that may be the reaction system, or that may be some control mechanism therein. Based on that and the experience or the correlations which are already available. So, for example, in some cases, we may require the drag correlation, in some cases, pressure drop correlations, which may already be existing it out, or maybe the turbulence correlation. So, if we combine these two things, we can write down the mathematical model, and this mathematical model then can be developed in terms of the mathematical equations, which are in general the differential equations therein. And since they are the differential equations, you require some initial and boundary conditions to solve those differential equations. And finally, we utilize numerical approaches to solve the mathematical model, which is combining the model and the equations therein, and we obtain the solution of this system. And so this overall process can then be repeated it out, and the accuracy and the improvements in the model can be done based on the reiterations of the processes therein. We may look at this one of the example in case of the industrial production and simulations, where the modeling process that is well connected with the production as well as simulation. So what we see that the first call row suggesting is that there is a production process, and this production process can be controlled by some processing parameters, where in that manufacturing process can be manipulated it out, and we finally obtain some process, some signature, some products therein. The important point is here like how we can analyze the manufacturing process, and so that we get a good product and the efficiency of the manufacturing process as well. To start with, we utilize the modeling process, and the modeling process start with that assumptions as we discussed in the previous slide. And based on the assumptions and the existing law, we write down the mathematical model, approximate that mathematical model. It means that we try to convert the differential equation into the algebraic equation so that we can convert that into the computational model. In this case also, computational model also requires some input parameter, and those input parameter may be correlated with the processing parameter, and finally we get the output results. Those results should talk with the processes or the products or the signatures that we obtain at the end therein. So we can clearly see a good relation between the production process and the simulation process. In all type of the manufacturing process may be related to mechanical system, may be related to chemical or electrical system, any manufacturing process that can be correlated in a similar way. We have another example which is also widely utilized in many of the biochemical industries, and this is the example of industrially stirred and aerated bioreactors therein. This is also very popular in many of the real life utility things, maybe food products and the other accessories. And here that we have a bioreactor where in that some reaction is taking place, some chemicals, some mixing is required, so that we have some impellers therein that is attached at two different locations. This bioreactor can be also written based on the CFT model, and the results of for one of the case can be seen here. Uh, Now it requires like a how do we improve the operation of this, and so we need to first validate the actual model and the CFT model, and based on the validation, we look for that how we can control or manipulate the operational parameters, and so that the efficiency and improvement in the bioreaction process can be obtained herein. We can also see the another example of the industrial fermenter, and that is being downscaled by utilizing CFT approaches theory. In general, the industrial fermenters are very large in size and they require a high amount of the raw materials therein, as we can see on the left side image therein. If we utilize some CFT modeling therein, we can downscale this industrial reactor, and the improved design can be obtained as seen here. What we can notice here, some regions which are in the blue and the red regions therein, what we can see here that blue red region is converted to a small blue regions, and the blue region had been reduced to a large amount therein. The reaction system can take suitably place in this region, and this can then be utilized uh, for bio related or the fermentation processes at the large scale. We can also see the ideal reactors and the downscale reactor. The downscale reactor seems to be performing well in comparison to the large scale reactors therein. And the CFT model, which is maybe based on the Eulerian Lagrangian scale or on the DNS scale, the both can be utilized to obtain such simulate some results therein. Another very important application from the industrial point of is the slurry management system. The slurry management is like in most of the chemical, biochemical, and even in the mechanical system, mechanical engineering systems therein. We may find a slurry which need to be separated, settled down, and then properly like it need to be released to the environment therein. So for example, there is a reactor. In this stack, we have a slurry, and this slurry is being first sent through the pump to the decenter system, and in this case like we have some separation mechanism. We have separators herein, and they helps us like agitating, they try to avoid and separate the system. And then finally the liquid is being overflow, liquid is going on one side, and the particle suspended is going into the underflow tanks therein. In this case, like this is the some CFT simulation, and the design of the modeling of this can also be performed. As we can see, large number of the parameters they will affect the process therein. And in all these cases, the CFT helps us in finding out a good and suitable results therein. In terms of in the field of chemical engineering, we can see like this is one of the chemical industrial plant. We can see like it's a beautiful image, but in this case there are a lot of processes that are taking place, and each of the processes they require some optimal conditions, parameters, as well as safety. And so the process simulation in chemical engineering, that also or the chemical industries also becomes very important in all dimensions, maybe from research and development, process design, maybe planning, optimization, operation of the industry, training and education, and also in the decision making and the distribution of the chemicals or the product therein. Not only that, we see like the flows are also complex. As such, in these images, what we see as the drop, which is falling in the liquid pool or on the solid surfaces, and we can see different varieties of the images that we are being generated therein. This is not a situation of a single drop. If we have a multiple drops, you will see like the complex situations that may arise. Practically, it will be difficult to see what may be happening in these cases, but CFT tools will help us to find out individual or the local features of all these things, which are practically important in many of the real life and the practical example in the industrial example therein. For example, we have the left-hand side image here. What is showing is the collision of the two water droplets, and they are bursting on the soap bubbles therein. It looks like a glass or the surface, but as such, the drop is or the two water drops they are merging and bursting the soap bubble herein, and then the features can be observed on time to time. This is observed on the 9 microsecond scale from the camera. If we do the experiments here, finding it out at the 9 microsecond scale and such types of the situation would certainly be very difficult. But CFT will help us to find out in one simulations, lot of information can be obtained for such cases therein. On right hand side, we have a two liquid streams. They are merging, colliding, and so we can see like a at low flow rates and high flow rate. At low flow rate, we see something chain-like structures are formed, whereas at high flow rates, we see some droplets therein, some fins therein, and then we see some droplet formations therein. So we can say seeds are there, filaments and droplets are there, and as such, this looks like a fish-like structures. So chain-like and fish-like structures they are formed therein. In these cases, there are high dependent on the flow rates when the one feature is converting into the another feature, and some of the features may not be important. Obtaining practical information from the experiments is again difficult in such situations, and CFT may help us in these cases as well. Yeah. uh, from mechanical or the aerodynamic point of view also, there are various applications of the CFT, and various complex flow features are observed. And we can see like the leftmost column where we have the particles, the circular types of the particles, which may be cylinder, they may be spherical particles. And we can see different flow features or the streamlines are seen depending on the flow rates variations or depending on the velocity variations therein. These features finding out experimentally and setting visualization is very complex. As we can see in the middle column that the different features are observed as we increase the velocity, or we can say that in terms of Reynolds number therein. It is again the third image on the right hand side is suggesting that there are viscous liquid jet, they are rotating, but they have like the mixing objective is to enhance the mixing. But in addition to mixing, we also see some different interesting patterns they are formed. For example, there is a droplet formation, there is a instability, there is a liquid rim, and the seeds as well. While they all helps us in doing the mixing and other characterization, but the experimental visualization and finding out what may be the interesting regions in which that we need to focus will again be difficult therein. In a similar way, there is a flapping object type of the liquids, and in this case also we see like the different types of the flow structures that are obtained depending on the parameter AD, which is like here the flapping file flaps. So depending on this parameter, we can clearly see like as we increase that different flow features are observed, and these features can be written down in terms of like the Cormon vertex, which is the first image. We can have a inverted Cormon vertex as we clearly see the inversion of the first case, and then we have a 2p wake. P means the pair of vertices of opposite sign therein. So there are two pair of the vertices are observed therein, and then the D says as 2p plus c. So here you have a two vertices, and then there is a single vertices. So two vertices and followed by the single vertex. And so there are many complex features which we can visualize experimentally, but again quite difficult to do that. So coming out to like the computational fluid dynamics, that is the topic or the modeling that we require to do today. So computational fluid dynamics, as the term itself says, starts from analyzing the fluid dynamics. In general, fluid dynamics can have a three dimensions. One that may be the purely experimental analysis. We may also do that purely theory analysis. And then the third approach may be the computational fluid dynamics approach. In purely experiment, we get a segregated information at some limiting conditions where the experiments can be performed. And in a similar way, in theoretical or analytical approach, we can also get the limited results where the mathematical equations can be simplified to the limiting conditions. Whereas the computational fluid dynamics approach do not limit us to find out the results. And so all these three studies complement to each other, that computational fluid dynamics requires a validation or verification from pure experiments and pure theory, but the pure experiments or theory will not provide the exact complete information therein. And so the computational fluid dynamics, as we say, we require mathematics, we require some tools to solve the mathematics, and then we also require a linearization or conversion of the differential equation into the algebraic equation. So the computational fluid dynamics generally requires the fluid mechanics, that means the understanding of the physical problem and then writing down in terms of the conservation laws. It requires mathematics, as the conservation laws need to be expressed in terms of mathematics, mathematical relations, and those mathematical relations need to be converted into the simplified linear algebraic relations therein. Once we get a set of the equation, we require a computer programming to solve these equations therein. And so we can say CFT is nothing but a interdisciplinary approach where mathematics, engineering, and computer programming play a role altogether therein. So CFT is then we can say it is science, or we can also say art, as we can see like a visualization of the features. So it can also be said as the art of the prediction. Then what is predicted and how it is predicted is also important to know therein. As such, since we say like it is related to the mathematical modeling of the fluid dynamic system, and so CFT can basically provide us a transport processes related phenomena that can predict the transport process related phenomena, which may be like a fluid flow, heat and mass transfer, chemical reaction, and not limited to those only. It may be the electrical, magnetic, and so other systems as well. How it predicts that? It predicts by solving mathematical equation. Those mathematical equations governs the process, and then using numerical or computational approaches as the differential or algebraic equations need to be solved to obtain the local fields therein. So we require like a CFT provides both qualitative as well as quantitative predictions, and these predictions are given in terms of the primitive field. The primitive fields can be said as a velocity, it may be pressure, it may be temperature, or it may be concentration or other important parameters therein. So these primitive fields are obtained by mathematical modeling, which is nothing but the partial differential equation, numerical approaches, wherein that discretization and the solution techniques are appears, and then we require some software tools, and those software tools have the solvers, they have a pre-processing and the post-processing utilities there. And so CFT requires that the knowledge, the CFT practitioners should have a knowledge of all these three, the mathematical concepts, numerical concept, and the tools that may be utilizing it. From utility point of the view, that CFT enables us like a, for example, if you are architect, then you can design comfortable and safe living environment. If you are a army person, you can develop weapons and estimate damages. If you are a chemical engineer, you can maximize the yield from the equipments that are employed in the chemical industry. In case of the meteorologist, you can forecast weather and warn for the natural disasters. For example, we see like the temperature, we see about the rain conditions and all. In case of the petroleum engineers, we can devise the optimal oil recovery strategies. In case of safety expert, we can reduce the health risk from radiation and the other hazards therein. And in case of the surgeons, to cure the arterial diseases, for example, hemodynamics, and vehicle designers, they can improve the aerodynamic characteristics as well. And of course, if you are a practitioner, you can make a lot of money by selling the colorful picture visualization then. Yeah. So how much time I can take more?
It's okay. You can. We still have.
Okay,
Yeah,
just
you can
wait.
take few more minutes. That's fine.
Yeah. Okay, thank you. So CFT, as we have discussed, that it is like a some approach where we do the modeling and the modeling of the real systems, real applications, real processes that we want to analyze them. So we can say that CFT is nothing but the virtual experimentation, and those virtual experimentation are based on the conceptual designs therein. And so CFT enables to the scientists or engineers to perform the numerical experiments, which is nothing but the computer simulations in the virtual flow lab environment. And those virtual labs are nothing but the simulation tools. So, for example, there is a two images herein. The left image is the real experiment, and the CFT predicts the right image. We can clearly see that the both images are very well matching to each other therein. We can also see like a one real life example. There is a smoke plume from the oil fire in the Baghdad, and we can see like if we see this dark region, this is like the smoke plume therein. The CFT predicts very well. The Patnaik et al. They did the simulations based on some CFT tool, and we can clearly see if we do that, the qualitative features of them, we can clearly analyze the both comes out or both are matching out very well to each other. Even like they are having a very good region where in that the flume was not there. The image is not very clear, but those regions are here in this region therein. We can also see some different set of the example where the virtual experimentation and the conceptual design is utilized. For example, there is a case of the square cylinder. A square cylinder in two-dimensional reflects for nothing, but we can see the building towers therein. So we can analyze that when the building towers or the high-rise buildings are being made, what may be the impact of the air or the surrounding pressures on those buildings there. We can clearly analyze the red regions are the regions of interest, but then we also have the regions where are the low pressure zones are obtained. And further, behind the building, we can clearly see from the images like this that we have a very low pressure zone, and these zones always have to be avoided if we are designing the building. In a similar way, we can also model a complete city or the colony by utilizing the CFT tool. As we can see, there are some high-rise buildings. We have a low-rise or the houses therein, and then we have some small disturbances. Those may be also houses therein. We can clearly see like which of the regions will have a good airflow, and which regions will have the low pressure zone, which is not good for the living environment therein. And so the airflow features can clearly be observed therein. Data centers, computing centers are another important applications which are based on the conceptual design. We can clearly see that the data center units therein, and then the flow features, basically the air and heat flow features are shown in these images therein. Uh, like we have faced the COVID recently, and in that case also CFT helps us in determining that what may be the breathing issues or the airborne risk that we obtain from the persons that may be nearby to us. And so we can clearly see the regions of the interest, like how much distance we should have, and based on the time, if you are talking to a person for longer time, how much time that you can talk or how safe is the time. So we can clearly see when the time is 1 second, we have the particles which are injected from the mouth of one person is far away from the another person, whereas as the time is increasing, they are coming closer to the, so the person that who is nearby can get infected therein. Again, the safe distance which was designed in the coronavirus can also be very well predicted from the CFT. The virus that may be released from the person in front, that will go in the zone, but if the two persons are closer to each other, for example here, then the both may affect it therein. And so the safe distance that was suggested based on the simulations and experimentation, that was something like a 6 feet. So, and for cycling, it was roughly 60 feet therein. So this have like a many components to the CFT, that be the analysis, be scientific knowledge, the computer code, and then it again comes to us. And so it is we who should be knowledgeable to understand what we want to do. And once we get the results, whether they are the good enough results or not therein. And so we state the problem, we express it mathematically, we try to solve them out, and then we inspect the results whether they are useful or not therein. And so the overall CFT cycle can be expressed in the form that is shown here as definition, processing, flow computation, and bio post-processing therein. So I will skip this. Yeah, so the CFT activities can then be combined through this cycle, that we try to understand, we try to conceive the problem, we try to evolve the results and obtain some new information. We try to prove whether these information are good enough or not. Once they are good enough, we try to apply in practice therein. And so the complete CFT activities, they are very important in designing, development, and prototyping of industrial applications therein. Okay? So as we already discussed, like a CFT analysis process can then be written into some set of the steps therein, starting from the statement of the problem, followed by the mathematical modeling, and then we have a mass generation, discretization, and time. So we have a differential equations or the initial boundary value problem. We try to discretize them, convert them into the algebraic system, and these algebraic equations are being solved by utilizing iterative solvers therein, and CFT softwares. They try to debug, implement parameterization and all, and then finally we do the post processing and verifications therein. So at that time, I will just go quickly through last part. Yeah. So overall CFT modeling overview can be given with the sketch shown here that we require a pre-processing. So the pre-processing requires mesh generation, solid geometry generation. So we can say solid modeler or CAD modeling and the mesh generation. And then this pre-processing part is being utilized and the physics is covered in terms of the mathematical equations. These mathematical equations may be transport equation or any governing equation for the given problem, maybe mass related problems, so specific mass fraction, physical volume, maybe momentum related, energy related, equation of a state that may be additionally required, or maybe some supporting physical model. And these physical model may come out from varieties of the way depending on the problem, maybe turbulence, maybe combustion, radiation, or the other things therein. We further require the material properties, boundary condition and initial condition, and apply the solver setting. We get the results, and these results need to be post-processed therein. And based on the post-processing, if the results come out to be good, we try to analyze them again and we may remodel if there are any errors therein. Finally, I would like to just summarize my talk as the modeling and simulations, as we have seen lot of examples that play a vital role in analysis and in optimal design of industrial processes. Amongst many other tools, CFT is one of the promising and cost-effective approach for systematic evaluation of the processes and its designing therein. Open source tool, obviously, we are talking about the CFT tools. They give us flexibility so that we can account all the underlying physics in efficient manner. And that's of course since they are open source, and so we can utilize it as and when we require. And not to mention, but the quantum applications is featuring some enhanced edge of feasibility in those open source tools for CFT modeling and post processing analysis. I would like to stop with this. Thank you. And if there is any query, I will be happy to answer. Thank you.